Welcome to Spring LIB.
In this problem, we are given the overall reaction for the lead storage battery. In part A, we want to calculate the value of the standard cell potential given the values for the standard change in enthalpy and entropy. So we first need to calculate delta G since we are given values for delta H and delta S. We know that there is an equation that relates those three variables. And once we have that, we can use the equation that delta G equals negative NFE to find that standard cell potential. So first we have to calculate delta G at standard conditions, since we know the values of delta H at standard conditions, as well as the value of delta S at standard conditions from this equation. So delta G is equal to that given value for delta H at standard conditions, which is negative 315.9 kilojoules minus the temperature when converted to Kelvin is 253, and the change in entropy delta S at standard conditions is given as 263.5 joules per Kelvin, and we need to convert this into kilojoules by dividing by 1,000, so that when we cancel off units of Kelvin, we are left with units of kilojoules, which we can subtract. So when we plug that all in, we get a value for the change in Gibbs free energy at standard conditions for this lead storage battery, and that comes out to about negative 383 kilojoules. Now we know that delta G equals negative NFE, and so the standard cell potential is equal to the standard change in Gibbs free energy divided by negative NF. And we need to convert that value of delta G into joules so that we can get the cell potential in units of joules per coulomb or volts. So that's negative 383 times 10 to the third joules divided by negative N, and we see that 2 moles of electrons are transferred in the overall reaction, times Faraday's constant, 96,485 coulombs per mole of electrons. And so when we plug in those values, we should find that the standard cell potential comes out to a value of 1.98 volts. And now in part B, we want to know what the value of the non-standard cell potential is at 20 degrees Celsius when the concentration of HSO4 minus and the concentration of H plus equals 4.5 molars. So this time we use the Nernst equation since we are at non-standard conditions. We know that the cell potential is equal to the standard cell potential, which we found in part A, to be 1.98 volts. Then we subtract 0.0591 over N, which we said was 2, times the log of Q. And based on the overall reaction, we can see that Q, based on the aqueous species participating in that overall reaction, is equal to 1 over the concentration of H plus squared times the concentration of HSO4 minus squared. And both of those concentrations are equal to 4.5 molar. So therefore, Q is equal to 1 over 4.5 molar squared times 4.5 molar squared. And now we plug that all in and rearrange to solve for when we calculate out the non-standard cell potential for the lead storage battery at these conditions, it should be about 2.06 volts. And finally, in part C, we want to know why batteries often fail more on cold days than on warm days. Well, we know that on colder days, that means that the temperature is lower than it is on warmer days. And we know that temperature appears in the equation delta G equals delta H minus T delta S. And so if we decrease the temperature, even though the absolute Kelvin units of temperature can never be zero, if we decrease the temperature compared to a larger temperature, the effect will be that it is a negative temperature. And we are given temperature independent values for both delta H and delta S. And we see that delta H was given to be a negative value and delta S was given to be a positive value. So delta H is negative and delta S is positive. So if we drastically decrease that temperature on a cold day, when we multiply these two values together, that comes out to a negative value, and we are subtracting that negative value. So we are adding a more positive value as that temperature becomes lower from a constant negative value for delta H. And so that would eventually lead to an increase in delta G where it would become positive. And now we know that delta G is equal to negative N F E. So that E is equal to delta G over negative NF. We just saw that when we decrease the temperature, we increase delta G. And based on this negative sign and this equation, when we increase delta G, we decrease the cell potential. And if the cell potential is decreased to the point where it's zero, then that is when the battery fails or dies, because it no longer has any potential for that reaction to proceed. And so that is why batteries fail more in colder weather, because as the temperature increases, delta G increases, which means that the cell potential decreases.